Hi, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. Today I'd like to give you a brief description of how to use an oscilloscope to look at signals. Now, every oscilloscope has many and varied capabilities and utilities, but they all have pretty much the same basic purpose and adjustments. Now, my plan today is to help you learn how to use the basic capabilities of an oscilloscope or scope to look at signals. But first of all, what is an oscilloscope? An oscilloscope is a device that allows us to view signals in the time domain. That is to say, we are viewing signals as they look relative to what they are doing as time progresses. Now, the oscilloscope does this by causing a line to move from left to right on the display in a specific amount of time, and then wiggling that line up and down in cadence with what the signal is doing. Now, there are two basic kinds of oscilloscopes. There's the old analog type oscilloscopes, and then there is a myriad of various kinds of digital oscilloscopes. Now, the analog types process the signals purely through analog circuits and create the display using analog methods. The digital types have an analog front end or input circuitry, and then the signals are digitized and processed, and the resulting data is then shown on the display. Now, as far as implementations, well, there's all kinds of implementations out there, from the ancient boat anchor types. Some of them are this wide and this, I can't even get it on the screen, this tall and way deep and almost a two-man lift. Those are the old Tektronix 545 and 535 scopes out there, all tube-based. And then there are their newer solid-state cousins, which are much smaller, but still they use a lot of the same display technology and so on, through to the digital types that are standalone and are much smaller, one little handle, all the way through USB units that use your computer as the display. Now, one quick note here, as if you were to go out on the internet and look for oscilloscopes, you're going to find, oh, well, this is a 25 megahertz scope, and this one is a 100 megahertz scope, and this one is a 200 megahertz scope. And you say, well, what on earth does that mean? Well, let me give you a quick explanation. If I had a 25 megahertz scope and I had a 10 volt 25 megahertz sine wave signal that I wanted to look at on that scope, that 25 megahertz scope would display my 10 volt signal as a 5 volt signal. It's half the size. It's what's called the 3 dB point. And so if you want to look at 25 megahertz signals and measure them accurately, then you're going to need an oscilloscope with a significantly higher frequency rating than 25 megahertz. So just a word to the wise, when you're looking at scopes, that's what they mean by 20 megahertz or 25 megahertz or 12 megahertz or 200 megahertz. So what makes up an oscilloscope? We need to have a quick tour of the oscilloscope, talk about what makes it up, the basic components. The first one is that there is some sort of display. That's what you as the operator are going to be looking at and using to make your measurements. There's the vertical input and controls, so that's where you're going to put your signal in that you want to view and control how it's displayed on the screen. And then there are the horizontal controls. Remember, I said we're running a line from left to right on the screen in a specific amount of time, and so the horizontal controls control how fast that happens and when it happens and so on and so forth. Now let's talk about the display. I did say that the old analog scopes used an older methodology. It's called a cathode ray tube, and what they do is they shoot a beam of electrons at a phosphorescent screen, and They have horizontal and vertical deflection plates, and as that beam goes through those horizontal and vertical deflection plates, they vary the voltage on those deflection plates to make that electron beam go in where they want it to go. And so by varying the voltage on the vertical, they make it go up and down. By varying the voltage on the horizontal, they make it go left and right. The newer oscilloscopes use some sort of modern solid-state display, such as an LCD or LED or other such thing. And the USB-based oscilloscopes will use your computer as the display. So let's take a closer look at a couple displays so that you can get a feeling for what the layout is and what you're looking at. Let's begin looking at display types here. Here's my old boat anchor Tektronix 485 oscilloscope, and you can see there are major divisions across the screen. There are 10 horizontal and there are 8 vertical, and if you look real close you can see smaller divisions on the screen as well. Those are 2/10 of a division for each one of those little marks. Now let's take a look at one of the at a digital scope. And so here's the digital scope here. If you were to count, you would find that there are 14 divisions left to right. But again, there's only 1, 2, 3, 4, 5, 6, 7, 8 vertical divisions. And you notice it has that same 0.2 division marks as well. Now let's look at the USB-based scope. And so this is a USB-based scope, so we're actually looking at the screen of my laptop. And you notice, again, it has divisions left and right. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 divisions. But notice again, 1, 2, 3, 4, 5, 6, 7, only 8 divisions up and down. And I don't know that we can easily see this, but if we look closely you can see there are the divisions there, the smaller divisions, and it's not real easy to see because of the Moore patterns. There are divisions on the horizontal, which again are 0.2 divisions per mark. So let's take a look at the vertical input of the scope. Now, the vertical input is where you usually connect your signal to the oscilloscope in order to see the signal on the screen. Now, the vertical input has both a resistive and capacitive impedance. There are specific characteristics associated with it, and very often these characteristics are posted right next to the input connector of the scope. And usually that resistive part is about 1 megohm. The capacitive part of that impedance will vary from oscilloscope to oscilloscope. Now, when connecting your signal up to the oscilloscope, you could directly connect it up using a BNC connector, because most oscilloscopes use BNC connectors for their inputs. But you can also choose to use a scope probe. I have 2 different scope probes here. You could use a scope probe. Now, one end of the scope probe connects up to the oscilloscope. The other end is what you connect up to your signal that you're trying to test. And a little note, when you're connecting your scope probe up, the first thing you always connect is your ground and then your signal. Now, scope probes come in all kinds of varieties. You can get scope probes that are ×1, which means if you have 1 volt connected to the end of the probe, the oscilloscope sees 1 volt. You can get ×10 probes, which means if you put 10 volts on the scope probe input, the oscilloscope only sees 1 volt, so it divides the voltage by 10. Now, when you use a times 10, you have to be mindful of the fact that this probe has to be matched to the input characteristics of the oscilloscope, or you won't necessarily get accurate measurements. It's going to skew things. And to make sure that it matches perfectly, you have to do what's called compensating the probe. It's an adjustment you make prior to making your measurement, and I'll show you how to do that later. There's another advantage to using a times 10 probe. Remember, the input characteristic of the oscilloscope is only 1 megohm plus some capacitance. But if you're using a times 10 scope probe, that is significantly increased. You now have a 10 megohm input. So there are advantages to using scope probes as opposed to directly connecting up to your oscilloscope. Now, what kind of controls are associated with the vertical input of the oscilloscope? Well, there are 3 basic ones. There's the volts per division, there's the coupling, and there's the vertical position. Volts per division, do you remember how I said that they wiggle the line up and down in cadence with the signal you're looking at? Well, this is how we adjust how far it wiggles that line for a given signal. So if you set this for 1 volt per division and you put 1 volt signal into the input, then it wiggles the line just 1 division on the screen. The second control is the coupling. It has 3 positions. Usually there's AC, there's ground, and there's DC. Now in the AC position, it blocks the DC level and allows only the AC signal to get through. AC coupling would be used, let's say, if you're trying to look at a small AC signal that's writing some sort of DC level. Like, let's say you're trying to look at the noise or ripple on the output of a power supply. So you have a 24 volt power supply and you're trying to look at a signal that's 50 millivolts. Well, you're never going to be able to get an accurate measurement of that ripple if you're using DC coupling. So you use AC coupling, it blocks that 24 volt DC, and now you can jack up your volts per division to get a good view of what that noise and so on. Or maybe you're talking about the audio signal on the collector of a transistor. Now the ground position, what it does is it disconnects your signal from the input of the oscilloscope and takes the input of the oscilloscope and connects it to ground. That gives you a really good 0 volt reference in order to set up your initial trace position and so on and so forth, maybe to help you locate the trace. And then lastly is the DC coupling. This position lets both the DC level the signal and the signal itself through on the scope's display. And this is the position that is most often used. Now, lastly is the vertical position. Now remember I said you put it in the ground position so that you can get a nice 0 volt DC level, and maybe you're going to be measuring some positive voltage and you know it's going to be positive, so you can use the vertical position to position that trace on one of the lower divisions on the screen. Or you know that it's going to be something that's going to be up and down equally, well then you use that position to set the position of the 0 volt trace right at the center of the screen. So that's how that goes. Now that I've kind of described this, let's take a look at what these controls look like on some oscilloscopes. All right, now we're going to look at the vertical input. Here is the vertical input of my old boat anchor. Notice right here, it says 1 megohm, 20 picofarad. We have the volts per division. Here right now it is set for 0.5 volts per division. We have the coupling down here. Right now it's set to DC, and just changing it, just moving it left or right. And then we have the position control, which positions the trace up and down. Digital scopes are a little bit different on their inputs. You have the volts per division here, but you notice there's no marking here. And that's because as you change it here, the volts per division appears on the screen. We have the vertical position right here. And so if you look over on the left side of the screen, you can see a little marker moving up and down as I turn that control. Coupling is done usually through some kind of menuing. So we have here the coupling. If I push the button here, you see I have DC, AC, and ground. And now the computer one. Again, we have the same controls. We have this here is the position control, and then we have the volts per division. Right now it's set to 0.3 volts per division. And then we have the coupling down here. Notice that we have AC, DC, and ground. And so with this, you have to change position using your mouse. Unless, of course, you're someone with one of those touch screens. Okay, let's talk about the horizontal controls. On the horizontal side of things, there are three sets of controls. There's the time per division, there is the triggering, and there's the horizontal position. Now, time per division. You remember how I said that they draw a line across the display in a given amount of time. This is where you adjust how much time it takes that line or the trace to move from the left side of the screen to the right side of the screen on the display. You choose the time per division. There's usually, well, depending upon what you're talking about, my old analog scopes were all 10 divisions from left to right. The one digital, my USB scope is 13 divisions left to right. My other digital scope is 14 divisions left to right. But there you go. This allows you to define how much time it takes the trace to move one of those divisions. So if you set it to 1 millisecond per division, and there are 10 divisions wide on the oscilloscope, then it takes a total of 10 milliseconds to move from left to right on the screen. If it's 14, then it's 14 milliseconds from left to right on the screen. By choosing the right time per division, you can accurately measure the time-related characteristics of your signal. Now, the tricky part is triggering, and that's the reason why I came up to the whiteboard here, because it needs some illustration in order to understand that. Triggering is what determines exactly when to start the journey from the left side of the screen to the right side of the screen on the display. It allows you to choose when, how, and based on what signal that journey begins. Now, you can choose the source of this signal. You can choose a particular input, vertical input. A lot of them will let you choose, let's say, AC line. If you're trying to see if this is AC hum on something, you might want to use AC line. Some oscilloscopes have an external trigger input where you can take a separate signal and connect it up to the front of the scope to trigger on that signal. Or you could choose, let's say you're trying to watch a signal on channel 1 of the scope and trigger on channel 2 of the scope. That's kind of essentially the same as an external trigger input on the scope. So you can choose the source of this trigger that you're interested in. You can also choose the slope. And now this is an important point because many times you do care about the slope. So what on earth does that mean? Well, let's say we're looking at a square wave signal here. This is the positive slope, this is the negative slope. And if you wanted to make sure that you triggered on the part of the signal that is going from a low value to a high value, then you would choose the rising edge or the positive slope. If you were interested in seeing what was going to happen when it's going from a high value to a low value, then you would choose the falling edge or the negative slope for your triggering. So that's the slope, is which edge, what direction is the signal going at the time that the trace begins to move from left to right. And then level. Well, let's say we have, instead of a nice square wave here where it's a little bit harder to define, let's say we have a signal that's more like this. And you say, well, I want to trigger on the positive slope, so we're going to choose a positive slope. But with level, you can choose where on this slope you want the trigger, the trace to begin moving to. So you can by changing the level, change where this trace begins. And then lastly, you have the mode. The mode is there are generally two kinds of modes. There's the auto mode where the scope kind of looks at the signal and does its little thing and decides, well, I think this is where we want to trigger, and you don't have a lot of you might have source and slope, but level and stuff like that is not always well defined. Or you can have what's called normal triggering. That puts you 100% in control. And a lot of times when you're just starting to try to see a signal, you might want to use auto mode to just kind of get to the place where you can actually see the signal, and then switch over to normal mode to more precisely choose how that signal is displayed on the screen. And the third control, like I said, is horizontal positioning. So you might have this on the screen here, but want to slide it over. Let's say you want the a gradical or a display gradical to fall right at that point. Or let's say you want it to fall exactly at this point right here, so that you can easily measure the amount of time it takes for that to go from this voltage to this voltage. Well, you do that by using the horizontal control to move this trace back and forth on the screen to accurately line up this point on the trace so that you can see how far it has come. Now, let's take a look at some horizontal controls on some scopes. All right, now the horizontal controls. Well, the first one and the easiest one on this guy is the time per division. And you can see it says microseconds here, and then it says 20 here. That means that is 20 microseconds per division. And as you change this, it changes how fast or slow the trace goes across the screen. And then triggering. Oh yes. Remember I said there was auto trigger, normal trigger, auto trigger, normal trigger. We have the trigger slope right here, plus minus, and the trigger level right here. There's also a coupling on this as well. You can have different kinds of coupling on your triggering too. There's DC and AC, low frequency reject, high frequency reject, and then source, internal, Internal goes back, in this case, way over here. You see where it says internal triggering, normal, channel 1, channel 2. You choose which channel it gets the triggering from. This one has line as an option for triggering. It has external, and this one has a connector for an external trigger, or external divided by 10. So if you put a 10 volt signal in, it's operating on a 1 volt signal internally. Oh yes, almost forgot the position control. So this varies the position horizontally on the screen. Alright, now the digital oscilloscope. Here we have the horizontal right here. And again, just like with the vertical, there's no numbers around here, but when you change it, you notice here you change the you change the knob, and it's displayed on the screen what you have. The positioning control is right here, and it tells you how much you're changing the position of the trace on the screen. And then you have trigger. You have auto, you have normal. Single is really nice if you're trying to catch a single event that's occurring that you want to see, and grab it and hold on to it without it going away. Now to set up your trigger, you have to push the setup button, and then over here you get to have your edge, positive edge, negative edge, and then it's got a whole bunch of other goodies on there. So I'm saying I want edge type is edge, and then rising or falling edge. We have the source of the trigger, channel 1, channel 2, external, AC line is all there. And then over here, underneath here, you can see the level adjustment for choosing the level of the trigger. And in this case, this scope will show you what level you're setting the triggering for. And with the USB based one, well, this one has the time per division over here, and you select the time per division by clicking on one of the buttons. Right now it's 0.1 milliseconds per division. I could make it 0.2 by clicking on that. And then you have the triggering controls down here, whether you are triggering or you're not triggering, what source, channel 1 or channel 2, whether it's a rising edge or a falling edge, and then the trigger level, the level at which you're going to be triggering. You notice down here, this level right here, it actually is telling you what the voltage level is that you're triggering on. So there you go. There's the tour of the various controls of the oscilloscopes. In our next video, we'll actually be talking about how to go about making the measurements using an oscilloscope. Until then, thanks for watching. Toodaloots.